Okay, so the first thing I want to point out is there is a Flux users group meeting, which will be a lunch. There's a link there. I just put into the chat. It is on April 16th. It's going to be down in the Henderson Room in the Michigan League. I highly encourage you to come to that. You'll be able to come and just kind of chat with a bunch of us and ask any questions you have and speak with other users and be pretty informal. We'll feed you guys lunch and you can come hang out with us for a while and get an idea of how things work and some other stuff people are doing. Also, any questions you have when you're going through this that can't be resolved during this session, or you run into issues later, please send them, the ones that are related to us, at hpc-support@umich.edu. And we're going to go ahead and get started. So we're going to cover the two different storage setups that are available on systems. There's two main ones that we care about. There are the fast ones, which is on the website here under the high performance storage, Lustre. And then there's the kind of normal ones. So you have what we call your home space. There's two different home file systems. And they're just a regular NFS mount. If you don't know what that is, don't worry about it. But they're kind of a typical network attached disk. We consider it more reliable in terms of, won't eat any of your data than the other systems. It's not backed up. Nothing on the cluster is backed up. Nothing provided by any storage that's provided by the staff here is backed up. So anything that you want backed up is your own responsibility. So your home space is just kind of like, that's where I keep like my source code and my executables, things I consider important. Most of the time, though, I'm working out of one of these high performance spaces, which is either no backup or scratch. So let's actually talk about the differences between those two in a moment. But they're the fast ones. They're built out of a piece of software called Lustre, which is used by some of the largest supercomputers in the world to hit extreme speeds and performance. We haven't lost any data on it yet, but again, it's not backed up. It's a little less mature technology than NFS. So we haven't lost anything yet, but I feel more comfortable personally about keeping stuff that's really hard to reproduce. I keep it all on home. Now there is a third option for people who want shared access, and that is storage you can get from ITS called value storage. Basically, this is an NFS disk you basically rent by the terabyte, and we will mount that directly on the system, so you can access that from all the compute nodes on the cluster, both Flux and NICs. And it's a really nice service. It's a very reasonable price, and they do have a replica disaster recovery copy available service also. We are also open if you have your own storage. We do have a number of strict requirements that it must meet before we will mount it, but if you do have your own storage, talk to us and we may be able to get your own storage directly on the cluster. Okay, so what we're going to be talking about today mostly is these high performance storage. So there's two different ones. There's Scratch and No Backup. They're both built out of Lustre, which is what we call a parallel file system or a clustered file system. It looks like a single file system to you as a user, but it's actually broken up into multiple pieces, and understanding those pieces is really important for getting a good performance out of your application. Now the question is, who has access to Scratch and who has access to No Backup? No Backup is available on NICS login, NICS, and Flux. It is funded by the College of Engineering, so it is only available to engineers. No Backup has been around for a while and has medium to good performance. It's better performance than home, but it's not as good as Scratch. Scratch, on the other hand, is part of Flux only, so it's only available on Flux login and the Flux compute nodes. It is available to everybody who has a Flux allocation. So a lot of what I'll show about the details about how Scratch works, because we'll focus on Scratch now, will apply to No Backup also. But realistically, if you're using Flux and you have access to both No Backup and Scratch, which one should you use? Use Scratch. So let's quickly run down the policy behind Scratch. It's all documented here on the Scratch webpage. Basically, you only get access to Scratch if you have an active allocation on the cluster. If your allocation expires, you will lose access to your data on Scratch. So what do we actually go through here? You say here, it is not for long-term storage. So 5 days after your allocation expires, this is the thing that lets you run jobs on Flux, you will no longer be able to read data out of Scratch. We won't delete it yet, in case there was just a mix-up between administration or whatever, or funding source. We won't delete it. We won't delete it for 60 days. But 5 days after your allocation expires, you will no longer be able to access that data. If you had a hiccup and you're still trying to get some stuff off of there, let us know. We can temporarily grant you access, but basically don't expect to be able to access stuff in Scratch after your allocation expires. But again, it's not deleted. 60 days after your allocation expires, we will delete the data. So between that 5 days and the 60 days, the data is still there, but you can't see it. So if you need to get at it, you just need to ask us for permission, and we'll grant you access to it. Or if you get a new allocation, so say you ran on the system for a while, and then you ran into a hiccup where you had to run back and redo your code, so you let your allocation expire, and then 10 days later, so more than 5 days but less than 60, you're like, hey, I want 100 cores. You get that 100 cores, you will get access back, and all your data will still be there. So after your allocation is put back into place, everything will be put back into Scratch. So what happens if it's been more than 60 days since your last allocation? Your data are gone, but you will have access to Scratch again. So you'll be able to write and put there what you need. So what this means is you will want to remove data from Scratch regularly, especially close to the end of your allocation and when your allocation is over with. Otherwise, you may lose access to it. Okay, so that's really the only policy. So I'm going to actually give you an idea of the layout of how Scratch works. So Scratch looks like a single big disk with over 340 terabytes of storage. But it really consists of 16 disks with some amount of storage each. Uh, 21.3 terabytes. So what happens is we have multiple disks that each can hold 20 terabytes of data, and then we have another disk, and this is what we call the metadata server. What happens is these are all connected together on the network. So if you're running on a node here and you create a file in Scratch, what happens is it first talks to the metadata server and gets the file name, and it will tell you where you can write your data. And then the client talks directly to the disk that it was assigned to. So what can actually happen is if one of these 16 disks gets full and you're assigned to that disk, you will actually get an out-of-space error. And what's neat about this is that IOs are independent. So if I'm writing to disk A and you're writing to disk B, we actually don't run into each other. But for small files are very, very bad for this kind of system because every file has to live over here on this metadata server. And so it basically looks like a database. It has to be really, really fast for serving up small files, but it is a single point of choke. We have 16 of these disks right now that actually store data. We can basically stick on, I believe the maximum we can have is 1,024 of them. Obviously that's requires funding and everything else to actually pull that off, but we can keep sticking on disk, and we actually plan to, as Flux grows, we will also grow Scratch and add more of these 20 terabyte units, and it will just grow the size and the speed of the system as we add more and more disks. So what actually happens? Actually, let me do this a different way. So what would be really nice is if I had a file, so I have this nice big file here, and say it's a gig. What would be really nice is if I could take one portion of it and send it to one of those disks, and take another portion of it and send it to another disk at the same time, thus doubling the size and performance of the system. Lustre actually lets us do this, and so this is what we can do on Scratch. And so we'll demonstrate that. So if we actually go and look at a terminal on Flux here, so I've got a PBS job, an interactive job, running on Flux. I've got 64 cores, and I am inside Scratch. So here's how the file structure inside Scratch looks like. I need to CD to Scratch, and then it's by project. So I'm going to use the support Flux project, which is like your allocation of CPUs, and then I go into my username. So if I look in just that project space, I will see everybody who has access to support. These are all the support people around campus. I may have access to multiple spaces. So I have access to multiple allocations, so that means I can go to my other allocation, Brock P Flux, and then my location. I'm the only one who has access to it, so there's only one user's directory in here. So it's /scratch/project/user. So if you're in multiple projects, because remember how, like, when the project expires, the allocation expires, you lose access to it. You lose access just to that project space. If you're working on more than one project, you'll still have access to the project that's still active. So it's important that you keep data for the two different projects in their respective locations. So I'm going to go back to support Flux. And so something I want to do is I want to demonstrate. So I'm going to run a tool over here. And what this is actually going to do is going to demonstrate the performance of the actual file system. So this is the client representing Scratch. This node right now is writing about 3 megabytes a second and reading 10K. I have a code here that just writes a large file at once, and it's an MPI application. So I've got this directory here. Let's go ahead and take a look at it. So if I run this LFS command, it'll actually show the underlying disk. So here I see for all of Scratch it is 341 terabytes, of which 93 are used, and there's 244 free, giving a total of 28% in use. But remember those 16 disks? So here's those 16 disks. See, they're each 21 terabytes, and they are all in some amount of moderate usage, and they're mostly free. As you can see, if you total these up, you get these numbers at the bottom. So what happens if I make a file here and then I use a command lfs get stripe on that file? It's going to actually say, hey, this has a stripe count of 1, and we'll explain what a stripe is in a moment, and it is assigned to disk 13. So the actual data for file A lives on disk 13. Now what happens if I make a file B? Whoops, okay, I guess file AB. See, it is now on index 3, so it is on disk 3. So of my 2 files in here, One is on disk 13 and one is on disk 3. So if you're just doing moderate sized I/O, that is, your files are a megabyte or larger, but they're less than, say, a few hundred meg, you probably want to stick with the defaults and not worry about this. And as you write files to a directory, they will automatically be spread across these disks. So as you're reading those files and writing those files from multiple processors, they will actually be independent from each other in terms of the I/O path and network path to the server they actually live on. So you don't have to worry about a bottleneck contention. The only thing you have to worry about a bottleneck is that metadata server, where you have, if you're doing a lot of open and closes of files really quickly, you're making lots of small files, you're basically going to go at the speed of that metadata server. So let's actually go ahead and run this. It's going to just run on 2 CPUs. Let's make a file 1, and let's write 10 blocks to it. So we'll actually see over here, see the client, how it jumped up to 42 megabytes a second. It actually wrote that file at 400 megabytes a second to a disk. So I've got this file 1, it's 80 megabytes, and it wrote it in 2/10 of a second. Let's try that again, and let's increase that file size a little bit. Let's go 5 times larger. You can see there we have 500 megabytes a second. The fastest speed you will see on Scratch from a single compute node is about 1 gigabyte. That's not the aggregate speed of the whole system. The aggregate speed of the whole system is about 5 gigabytes a second, and that will vary based on the kind of I/O happening on the entire system. Now this was written from one host. What happens if I actually go and do multiple hosts? So let's go ahead and do let's do 24 processors, and let's increase the size here to 8. So now that I'm on 24 processors, this is actually running across multiple machines. This make ran program is actually a C MPI program that uses MPI/IO to write across multiple processors simultaneously. It's really nice. It's nice to not have to communicate data back and forth to a single processor to use traditional I/O, and you can get aggregate performance greater than what a single machine can provide. Now I didn't get that great a performance here because I'm having file contention issues, having multiple CPUs hit one thing. So it took me 30 seconds, and I got 316 megabytes a second aggregate speed. So I wrote this 9 gig file in 30 seconds. Let's go ahead and run git stripe on that file, and we'll see that it's still assigned to one disk. So let's look at, what if, this is a relatively large file, and what if I want to really speed this up? What I can do is I can do that striping where I go across multiple processors. Remember this? Where I've got the different pieces of the file going to different disks simultaneously. The way we do this is we use a command called setStripe. So LFS setStripe. If you run it by itself, helps if I could spell it right. If you run it by itself, it'll give you the documentation. But we're really most interested in this stripe count. What stripe count is tells the system how many of those 16 disks you want your data to be spread across. So what does this mean when you do this? You're going to be involving more disks. So if any one of them is operating slowly, you're gonna go with the slowest disk. It's just kind of how it works. But it's going to be the slowest disk times the number of disks, so your aggregate performance could still be greater. It really only makes sense for large files. So I would really only do this for 1 gigabyte, 2 gigabyte files bigger. What's the largest file I've ever written? It's like a half a terabyte. So a 500 gig file, that totally works. This also lets you, when those things get full, go across multiple things. So the way it works is we do LFS set stripe, and then we say the stripe count we want to have, and we see that we do that using the -C option. So we do -C, and let's spread this across 5 disks, and then you give it a directory. Now what will happen is that striping information gets stuck onto the directory. And so the existing files in that directory, they don't move, they don't change. So once a file is written, it doesn't get relayed out on disk. But when it gets stuck to the directory, any new file created in that directory will now be spread across multiple disks. So if I go back to Stripe, I touch file C, I will see that it now has 5 indexes spread across randomly across 5 of the disks. So what does this mean? If I go and delete file 1 and I run my MPI code again, it's now going to be writing across 5 disks simultaneously. And so our expected performance should be much higher. It's not continuous from all disks. As you can see here, the client wrote 400 megabytes in 1 second, but it took longer than that. And so the aggregate performance we got for this write was 800 megabytes a second. But it only took 11 seconds for me to write that 9 gig file. You'll notice I'm using all large file sizes here. Larger and fewer is always better. The bigger your files, the more aggregate performance you will get, and the fewer files you have, so the less often you have to talk to that metadata server or seek on disk to a new inode, the better off you'll be. Because these are all network file systems, and you have to talk over the network back and forth to get the file created and everything else, it acts a lot differently than the hard drive like in your desktop. Thus, it is always better to have fewer large files rather than more smaller files. So let's actually go ahead and run this on more processors. Let's crank up the file size. No, you don't need an NP because I'm running under PBS. So when I did NP, what I was doing, I was forcing it to run on fewer CPUs than I actually had assigned. So now I'm using all the CPUs. You can actually see here instantaneously this client wrote 800 megabytes in 1 second. So you might be asking, if these machines are just on 1 gig Ethernet, how are we writing 800 megabytes a second from a single client? Scratch does not go over Ethernet. Scratch actually uses the 40,000 megabit InfiniBand network that every Flux node has. And thus the performance from a single client is much greater than performance to no backup or home or value storage over a single client. That might change in the future, but for the most part we would always expect Scratch to be faster. So you can see here I actually broke 1 gigabyte a second with this write, and this is with the system doing other things at the same time, because we're actually, Flux is in use right now. There's only 16 disks. Everybody who's using Scratch is hitting that disk. So if I did the same thing on no backup, I would expect half the performance for something like this. It's just kind of the nature of the older equipment and going over gigabit Ethernet that you're just kind of in this situation. So what are some of the things you can do for doing MPIO? Let's actually look at the underlying C code, and the same things exist for Fortran. If I look at this make ran files, I'm using, let me find it, where's the, I actually use a command MPI file open. Again, you don't have to use this. Using MPIO and using Scratch are two independent things. If you're running a lot of serial jobs, and you each have, reading their own data, have them read it out of Scratch. Don't do any striping. Just kind of, let the system automatically balance your files across all the disks and just kind of let it do its default. Most users do not need to change the default and can just take their application and run on Scratch rather than home and see better performance. If you're doing crazy I/O that is very, very large, or you're doing an MPI application and you're communicating data back to a single CPU, maybe you want to look at using MPI/O. This is the low-level way of doing it. This is the raw MPI command. But basically there's an MPI file open. and then there's a file seek, which sets an offset in the file. So what's really happening here is I'm saying, okay, CPU 0, you're going to write from block 0 to 5, and CPU 2, your offset is 6, so you're writing from 6 to 10, etc. And you can use this get position to find out where you're currently pointing at in that file. And so this actually lets all the CPUs write to the same file from multiple computers simultaneously. So you no longer have to communicate back blocks of data and kind of write it a chunk at a time using traditional I/O. This is relatively low level. There's a number of other tools that I would recommend using instead. Specifically, I would look at using HDF5, NetCDF, or XDMF. These are all libraries for doing I/O. And basically, they give you a lot of nice features that you're not, I mean, they're binary files, but you get a lot more structure and metadata, so you can think in like, okay, I've got two matrices, they're called A and B, and they're these dimensions. And it will actually tell you that, and it will let you write matrices simultaneously, a chunk at a time. So you'll be able to take a matrix, take a piece of it, the piece that's on every CPU if you've decomposed it, and they will actually write those pieces to that one file simultaneously, all at once. It's really, really nice. A number of well-known applications take advantage of this parallel I/O, and it's really nice. So like, there's ways to run WRF using parallel I/O with NetCDF. There's ways of running Flash with both parallel NetCDF and HDF5. It's really, really nice. And they're just regular files when you're done. You don't have to read them using MPI calls. They're still, like, if you used a regular MPI I/O commands, they will be readable using a regular post-processing tool that reads a binary file. HDF5, a parallel written one, will look just like a serial one. And so you'll be able to read that in MATLAB, IDL, Visit, ParaView just fine. Same with NetCDF. A parallel NetCDF file acts and looks the same way as a regular NetCDF file. Okay, so we have a question here. How is file striping affected by having multiple machines accessing the same set of files? Okay, so good question. So if you have, okay, let's kind of sketch this out. Let's get a, okay, so basically you're saying is you have job A, job B, job C, and job D. And then you're going to have file 1, 2, 3, and 4. If you're going to run all these jobs simultaneously, it might be better off not to stripe these, because what will happen is each one of these will be in their own disk, right? On average, they'll be spread around all those disks, the 16 of them. And so under that situation, each of these jobs accesses their files and they're on their own disk. Fine. This is the default behavior. On the other hand, what if we have all of them are kind of accessing the same file? And this is like, say this is a single large file. This you may want to stripe. And depending on how you access the other ones, you might want to also. You'll really just have to mess with it and see what you kind of get for performance. I would, if you've got multiple files all being accessed at the same time by multiple jobs, you probably want to not stripe as much as you would as if you were accessing a single file at one time. If you were just checkpointing an application, like you run for a while and you're going to write one big file all at once, definitely stripe. If you're accessing all of them kind of in random, you probably don't want to stripe as much. Does that answer your question? So the last thing I want to mention is, so for most people, you don't have to worry about these issues. If your I/O size is moderate, just a few megabytes, go with the default. Don't use any of the set stripe or get stripe commands. Don't don't bother with them. If you're doing really big things, okay, then maybe you want to start striping. I tend to stripe about 1 stripe per gigabyte on nobackup and about 1 stripe per 2 to 5 gig on Scratch. In general, running your applications out of Scratch or nobackup is preferable to running it out of home, and running it out of Scratch is preferable to running out of nobackup. The policies behind the systems are all documented on their corresponding web pages on our website. Remember that you get space in Scratch only if you have a flux allocation. After an allocation expires, you will lose access to that data after 5 days, and 60 days after the allocation expires, we will delete the data, so you need to move data off. So one thing I want to mention about that is ways to move large quantities of data. The login nodes have a policy that any application running more than a few minutes gets killed. Just basically keeps machines from being crashed from people running testing jobs that are overloading the system. So what we have this introduces a problem that when you try to transfer large files, SCP or rsync will run into issues of they'll run out of CPU time and your transfer will keep getting killed off after moving a few gig. Our solution is we have transfer nodes. Transfer nodes are dedicated nodes. They look just like a login node, but you can't log into them. So that's one big difference right there. But they don't have any of these differences. So the other things they do is they let you run SCP against it, no problem, without any CPU time limit. So basically you want to do all your SCP commands and SFTP against flux.exfer.engine and nix.exfer.engine. This is actually getting upgraded. These will be 10 times faster here in a moment. And flux.exfer is connected by the 40 gigabit network to Scratch. So in theory, when this is all done, you should be able to download data at a gigabyte a second if no one else is using it and your host can consume data that fast and has a fast enough network connection. To use these services, you need to get what's called an M token, which there's a link to here. You might have seen these things before. They look like a keychain with a 6-digit number that changes over time. Go to the Entree office. There's one on North Campus and there's a couple on Central Campus, and just say that, hey, I need an M token for accessing the Flux system and the Nix system, and they'll give you one. There is a way to transfer files without needing that, but it's a little bit more involved. Is you can use Globus. We have documentation on that. There's also another video tutorial which we've done before. Here's a quick one I did here. This is a web-based system where you actually set the file transfers from a website, but you do need to install a small piece of software. I have mine running right here to be able to transfer files. Globus should be more reliable and faster than SCP, all things being equal. But it is different in using SCP, but it also doesn't require an M token, so choose which one you want to go with. I highly encourage all of you to get M tokens as soon as possible. Sometime in the future, we will require M tokens for even just logging in and submitting jobs. So you may find yourself, of course we'll announce this before it happens and when we will do it, but it's just a good idea to go ahead and get the M token now so you can start using the transfer host, and then you'll be all ready when we start requiring it for logging. Okay, that's everything I had. The only thing I'd like to remind you is to check out the Flux Users Group Lunch. You should have all gotten an email with a link to this in it, but otherwise I put it into the beginning of the chat box. At this point, just go ahead and put all your questions that you may have. Okay, so the question is, are files transferred via GridFTP encrypted while in transit like files transferred over SCP? Not currently. There will be a way in the future to do that. Credentials are always encrypted. If you have a need to move a very large quantity of files where GridFTP looks better, talk to us. There's a command line way of making this all happen. So there is a way to do it, but by default you cannot, and it is not obvious how to make data encrypted. Most of the time, though, when you think about it, your data doesn't need to be encrypted. Only your credentials need to be. Also, data through the Globus system is, if you're going between a machine on campus and Flux, I mean, your data never leaves the campus network. Other questions? Looks like we have one coming in. Okay. Well, Oh, that's a very good question, and actually we haven't discussed that. That's something we'll consider, and we'll let you know when those come into, when we put the tokens into circulation, we may do it. Right now, the way you log into a cluster from off campus is to first either start up the VPN client, which you can download from ITS's website, or you can first SSH into like login.itd or login.engine, and then SSH into Flux or Nix. Any other questions? Okay, well, again, I encourage you to attend a users group meeting. If you have any questions, the support email is hpcsupport@ums.edu. And this will be up on the YouTube page, which I had pasted in earlier. And that is everything I have. Thank you very much for attending.